So the basic theorems or basic properties of Boolean algebra is these are the four ones. One, that if I want to do an operation with 0, then the OR operation. So I'll quickly write the truth table of and OR. So this is a truth table of and. This would help me A, B, and let us say the output is Z. 0 0 0 0 1 0 1 0 0 1 1 1. Now similarly for OR gate also, if I write A, B, and Z, 0 0 0 0 1 1 1 0 1 1 1 1. Now I am saying I want to do an operation x or 0. What is the output? So let's say this is the x, A is my x, and if I am operating with 0, so if x was 0, A was 0, and I am doing an OR operation with 0, output was 0. If A was 1, I am doing OR operation with 0, again it was 1. So that means whatever was the value of A, and if I am doing an operation with 0, I am doing an OR operation with 0, the output was also A. And this is what is written over here, that if I am doing an OR with a 0, then variable will remain same. Similarly, if I am doing an operation with 1, my output is going to be 1. So I am saying either variable x or 1. So that means whatever is the value of x, whether it is 0 or 1, my output is always going to be 1. Similarly, we can also see the operation with 1 for the AND gate. If x, whatever is the value of x, if I am ANDing it with 1, the variable will remain same. So let's say this A is x, so I am doing an operation with 1. So if A is 0 and doing an AND with 1, output is 0. If A was 1 and I am doing an operation with 1, the output is 1. So that means this A remains same if I am doing an AND operation with 1. So on the other hand, if I am saying x and 0, so whatever is the value of x, my output is always going to remain 0. So that's how we can remember these operations. These operations are very, very important or useful whenever we are doing logic minimization. Now idempotent law, idempotent means like if I am doing an operation with itself, what is the result? So if I am doing an OR operation of x with x, means this A is also x, B is also x, both of them are same. So that means either 0 0, output is 0. If both of them are 1, the output is 1. So that means if the value of x, the output is also x. So x plus x would be x here. And if I am doing an AND operation of a variable with itself, the output is again the same variable. Involution law means that what would happen if I am taking invert of a variable, I am taking invert of a variable. So this value will remain, will bring it back. So inverse of a variable is again the same variable. So this is what involution law here says here. The other is law of complementary. Complementarily means that if I OR x with x dash, then output is going to be 1. So this means that if x is 0, x dash will become 1. So 0 or 1 will become 1. Similarly, if x is 1 and then x OR will become 0, x dash will become 0. So 1 OR with 0 will become 1. And x, if I AND with inverter of itself, or basically not of itself, then the output is 0, because if this is 1, then this will become 0, or if this is 0, then this will become 1. The output is this combination, which means that output is going to be 0. So these basic theorems is going to help us, and let's consider a couple of more basic theorems which are whether these operations are commutative, associative, distributive. So yes, they are commutative. That means any order will not affect. If we are doing an AND with x and y or y and x, it doesn't matter. Or operation, so which essentially means that if I am writing a AND gate, it doesn't matter whether I am writing in which order, whether it is A, B or C, or C, A or B, or B, A or C. So all of this, the order of these variables does not matter in either AND gate or OR gate. That's what law of commutative says. Associative means, let's say I have there are two operations which are in like together. So how does the order matter there? It doesn't matter. So means that if I am doing an AND operation of two operations which are already ANDed, so it doesn't matter whether I am doing in. So this is again the similar commutative expressions which is extended to more than one variables. It doesn't matter what is the order, whether I am doing this AND gate like this, or I am doing this AND gate like A, B, and doing another AND. So all of these things are equivalent. So all of these three are equivalent, whether we are creating only one AND gate or we are creating two AND gates. We are first ending A and B and then ending it with C, or we are first doing B and C and then ending it with A. So all of these three are equivalent. So that's what law of associative means. Distributive is more interesting. So basically, like this is a mixing of two operations. Now y plus z is we are doing a OR operation, and outside it's a AND. So that means if I want to AND the OR of y and z, so that means I can also do it in a AND of x and y, then it will be OR of x and z. So similarly for product also it will work. If we are doing x is being ORed with the product of y and z, or AND of y and z, we can also say x and y and ANDed with x or z. So this law of distribution means that if we have these operations like this, then we can reorganize these operations in the other order. De Morgan's law is a inverted law that essentially says that if we are making a note of an expression, then all its individual variable will be inverted, plus your OR would be converted into a AND. So here also it happened like this, that if we are doing a inversion of two variables, like and operation of two variables, then all individual variables would be inverted and this AND would be changed to an OR gate. So you can ask here one question, that why we are representing all of these in two different tables. Like you see a good similarity here. So similarity that whatever we are writing here is also written very similar way in this the operation with OR. So why it is happening? Because in Boolean algebra there is an interesting principle which is called duality principle. In duality principle, so before explaining this duality principle, let's understand one more fact, that when we started explaining this concept of zeros and one, when we are seeing these zeros and ones are essentially two different states of a matter. So there were various examples given, like in a magnetic disk, either it is magnetic or non-magnetic, or let's say spin of a electron, whether it is clockwise or anti-clockwise. Or similarly, let's say at one place if there is a light or there is no light. So similarly, we can see that everywhere we see two different states. One of the state we are marking as 0, another state we are marking as 1. So which state we should mark as 0, which state we should mark as 1? Does it have any kind of a impact? This is what this duality principle says. This duality principle says that we can replace wherever there is a 0 in a Boolean expression, we can go ahead and replace it with 1. But along with that, we also have to replace plus, means OR gate, with a AND gate, because 0 is an identity element for OR gate and 1 is an identity element for an AND gate. So if we replace all of them, then the function would remain same, the expression would value the same. So you can see some of these expressions. If we see quickly here, if we are ANDing, so if we are saying that 0 is converted into 1, 0 is converted into 1 and plus is converted into dot, the expression is same. Here also the plus is converted into dot and 1 is replaced with 0, 1 is replaced with 0, expression is correct and same. Here also plus was replaced with dot, means OR was replaced with AND, there was no 0 and 1, so we need not to do anything here. Okay, here also, so we have replaced this OR with the AND gate and 1 with 0, so it worked. This is how it was working. So we can see here also, like wherever we were applying, we just need to replace. Here there was a AND gate, this AND was replaced with the OR, and this plus means OR was replaced with the AND. So and then this expression x dot y will become x plus y, x dot z will become x plus z. So this duality duality principle says that the expression would remain same, like, but we have to do it on both the sides. The other interesting aspect of our duality principle is that, let us say, this would be very much exploited in De Morgan's law. So in De Morgan's law, whenever we would like to invert a particular variable, so let's say we want to invert a function f, then what we need to do is, inside we can invert all of its variables and replace AND with OR and replace OR with AND. So we'll take couple of examples. If not today, we'll take them tomorrow. So we'll see that how this duality principle can help us in minimization or in looking things in a different way. So one of the agenda of this understanding Boolean algebra was to minimize our expressions or to simplify expressions. So based on whatever theorems we have seen here, based on these theorems, now if I would like to use them, then I can create some of my simplification theorems. So these simplification theorems can help me directly in simplification. So let us say this is the expression which is given to me. Now what I can say is, because of a distributive law, I can write this as x y plus y dash. Y plus y dash, I know it is always going to be 1, so I can say this is equal to x. Now there are multiple ways of seeing this. Now again, using my distributive principle, so I can also write this as x plus x x plus y y dash. Yes. So if you want to expand this x plus y y dash using distributive So then this is how it will become x plus y and dot x plus y dash. So y and y dash is 0. So x plus 0 is equal to x. So you can see that although I am writing it in a longer way, but again because of simplification this is essentially representing only x, and this x plus y dash would actually represent x. So this simplification could be good shortcut whenever we are simplifying our expressions. The other one, absorption. So again I can take it like this. So either I can say x dot 1 plus x y, which is equal to x 1 plus y. 1 plus y is equal to 1, so it can be said as x. Okay, so this also either we can go ahead and multiply it x dot x plus x dot y, which is equal to x plus x y, and now we can use this principle. This will become x. In the other way, we can also say that x plus 1 and x plus y, and now because it is a distributed one, so this x is here, this x is here, so we can also say x plus 1 dot y. 1 dot y is equal to, this has to be x plus 0. So x plus 0, and now 0 dot y is equal to 0. So x plus 0 equal to x. This could be another way of saying this, but the overall idea is that, see, this particular expression has multiple variables, multiple of logic gates would be required, but after simplification you are left with only this variable. Now let's take the other one, elimination. So here I can say this is x plus x dash y, x plus y. Now I can also write it like x plus x dash and x plus y. So this is why, this is because of our distribution principle. Now because there is a plus here and there is a product, so I can say that I can first do OR with this, and then we'll do a product, and then this x and this y could be done using an OR operation. Now x plus x dash is 1 dot x plus y equal to x plus y. If I want to see this x dash plus y, I can simply multiply it out. I can say x dot x dash plus x y. X plus x dash is equal to 0 and x dot x dash is equal to 0, and this is x y, so that means this will become x y. Now what does these three simplification theorems are saying in a way? The first uniting theorem says that if I have a variable x and there is another variable y whose complement is present, is complement is doing an AND with itself, like the variable y as well as its complement is doing a product with doing an AND operation with this variable, so then that can be united. in absorption we say that if there is a variable x and any other expression which has x multiplying with or ending with some other list of variables, all of them could be absorbed in x. Elimination is an interesting one, because here x plus invert of x and then it is ended with y. So this could be this x dash could be eliminated, and we can say x, it is actually equal to x plus y. So I can understand this could be little confusing, so we need to do couple of examples ourselves, and then we would be able to understand these things better. So let's do at least one more. So consensus consensus means that you have variables x y as well as x dash z and y z. Now you see that this y is here and this z is here, so that means you have a variable, you have a variable x, and there is a multiplication factor here, and there is another multiplication factor with the invert of this x, and that multiplication factor is also doing an OR operation. So that means this thing could be eliminated. So this part could be eliminated. How can we eliminate that? Let's take an example. So let's try to prove it. We can say that x y plus x dash z plus y z. Now y z we try to create another one. We say this is also multiplied with x plus x dash, because x plus x dash is 1, so I am multiplying y z with 1. This will become x y plus x y z. I am writing it here, x dash z plus x dash y z. So x dash, this is y and this is z. Now here I can say x and y are the common part, and this is 1 plus z, and here I can say that x dash z is a common part, 1 plus y. Now because 1 plus z will become 1, so this is x y plus x dash z. So this is what we say consensus theorem. In consensus we are eliminating whatever was the multiplication factor with x and z if they are found like this. Okay, so now these let's say a couple of examples to see whether we can use them, and we can use them to simplify things. Now let's take this example, z is equal to a dash b c plus a dash. What should we do? So we see that this a dash is a common part, and I can see this as one entity. This is can be considered as one entity. So I can also say this as a dash 1 plus b and c is equal to a dash. So in other words, I can simply use this as this absorption theorem. So I can call this as absorption theorem, and using an absorption theorem I am saying that this b c can be eliminated easily. Now if we have something bigger like this, so what we see that this part, let me call x, and this is also present in the similar form like here, and d plus ef I see here. So this I can say y, this is also y. So I can write this whole z equal to x plus, this is actually y, x plus y and then x plus y dash. So I have x plus y, I have x plus y dash, so this will become x plus y dash, so this will become x. So this become x and my x is actually a plus b dash c. So this is how we can use all of these theorems to simplify. But in the end, I would summarize it like this, that yes, we have this n number of theorems and these theorems can help us in minimization of Boolean expressions. But we are not always sure that what theorem to be used. What if I missed the right one? What if I am not able to use the correct theorem, or can there be a systematic method? Okay, although we are going to use these theorems in those systematic methods also, but can there be a more systematic method? So those systematic method we'll try to see in tomorrow's lecture or in the next lecture. By then we'll try to use these theorems to simplify couple of more examples. Maybe I'll float a tutorial sheet along with this lecture, so that you can try it out, and maybe you can directly do some exercises from the textbook Roth. Thank you very much.